My name is Liu from Department of Material Science Engineering at Pennsylvania State University. I'm going to talk about fundamentals of quantitative predictive theories in this presentation. As we know that the human accumulated knowledge and the origin from empirical approach as reflected in the 3 ages of our history. We call it Stone Age, and that way we use raw materials, basically from nature. That of course took many, many years for us to master those tools. And in the Bronze Age, we started making man-made materials. It's copper, tin alloys, with two of the compositions, one 12%, 80% of tin, another 25% of tin. And then we have the Iron Age, which is based on the iron-carbon system. Of course, at that time, people do not know copper-tin, so to speak, but today we know that copper-tin phase diagram. From the copper-tin phase diagram, you can see that 12% of tin is meticulously stay in this area. Is FCC copper solution, this temperature range. And for 20 to 25%, is right in the range. We have a majority of the beta phase in this temperature range. By carbon phase diagram today, we know that we have a lot of phases forming from the BCC gamma phase, we call it, FCC gamma phase, now the BCC phase, then we have a lot of different structures, and like martensite, ferrite, pearlite, and bainite. And in my master's degree, the reason I got into material science was because when I took an undergraduate class in metallurgy, and my teacher told us that bainite is very interesting. So that's why I changed my major from metallurgy to material science back in 1982. And then we had the Industrial Revolution from 1.0 to 3.0, from the time like 1760 to around 1840, about 100 years. During this time period, we have the steam power. At that time, we established the thermodynamics, second law, and a little bit third law too. And then in the Industrial Revolution 2.0, we invented electricity, and then we had computerization. As we all know that today we are experiencing the Industrial Revolution 4.0, it's about the digitization of knowledge in order for the integration of cyber and physical space, so through systems, manufacturing, and materials. And if you look at this around 150 years since thermodynamics was well established, and see what we have learned in this 150 years. First, we know the classical thermodynamics by Gibbs. He established the equilibrium thermodynamics in the 1870s, so the exact 150 years about. And then about 30 years later, he invented or developed statistical mechanics in 1900s. And he published a paper in 1901. And then 20 years later, we invented the quantum mechanics, so Schrödinger equation. And then we have the quantum statistical mechanics, which is above the statistical mechanics by the classical statistical mechanics by Gibbs, it's by Landau and then other people about 10 years later than that. Then another 30 years, we invented density functional theory. And we now can, at that time, we can start to quantify Schrödinger equations or quantum mechanics. And at the same time, of course, the irreversible thermodynamics has been under development. If you look at the literature, it's probably mostly by Onsager and Prigogine in 1930s and the 50s. And in the 1970s, they came up with another approach to model thermodynamics. I call it digitization of thermodynamics through the codified modeling of individual phases. I want to mention another very important contribution by Max Hillard. Later, Max Hillard, he just passed away November last year. And thermodynamics with internal processes. And I want to emphasize that we have been using this tool and trying to revise what the irreversible thermodynamics developed by Onsager in 1930s. So what do we know? What do we do not know from theories based on those 150 years of scientific study? And I talk about here is, of course, we know many things, but I talk about the quantitative knowns for a physical system from theories. That means no experiments, just purely theory. We know that at temperature equals 0 Kelvin, from the third law of thermodynamics, entropy equals 0. Then from quantum mechanics, mostly density functional theory, we know that any system has a ground state. And we can calculate the free energy of that ground state. So there's a total energy and free energy from electrons and free energy from phonons. And we also know that when temperature rises to 0, the system is going to do some changes. But based on the second law of thermodynamics, any changes must produce entropy. That's called entropy production. And every irreversible spontaneous process will produce entropy because for the second law. And it means that both melting and freezing will produce entropy. However, what is unknown to us from theory is that, or theories, what is entropy at a finite temperature? Okay, because in order to fulfill the second law of thermodynamics, we have to be able to evaluate the entropy at a finite temperature. Turned out, even mostly, we could not predict it today. At least in the literature, we rely on measurements. We measure heat capacity, we do integration, we measure phonons. And then let's look at what's the difference or some relation between theories and experiments. As I mentioned, the Gibbs thermodynamics is for statistically equilibrium systems only. It doesn't apply to non-equilibrium systems. And then quantum mechanics, or DFT, it applies to ground state configurations. But when we do experiments or do observations, observe the stars, we don't do experiments on the stars, but we observe them, that we always find a transition between states, a non-equilibrium and equilibrium, or local equilibrium. And we also know that based on statistics, and we never do a measurement. We don't measure only one configuration. We measure the mixture of all possible configurations, which can be activated under given conditions. So now, that means we get a challenge here. Today, most of the theoretical predictions do not agree with experiments. We have to fit our model parameters to experiments in order to quantitatively predict the experiments or simulate experiment observations. We have to get the experiment input first in order to simulate observations. That means our prediction depends on experiments. Therefore, the question is, can unknowns be predicted theoretically and quantitatively? Of course, I give this talk, that means I believe we can. Okay, I think we're witnessing a paradigm shift towards knowledge accumulation through quantitative computational prediction and experimental validation. So I hope through this seminar, I can convince you at least that some of the properties we can predict without experimental input and quantitatively. So let's go back, talk about the three different group of theories. We talk about the Gibbs equilibrium thermodynamics and statistical mechanics and quantum mechanics and the irreversible thermodynamics. Now let's go backward. I mentioned CAFAD is part of the irreversible thermodynamics because it model properties for individual phases in terms of function of temperature, pressure, and composition, and internal degree of freedom. So internal degree of freedom is what defines a non-equilibrium system. However, because we're doing model, then we have to have the experimental input. Okay, same thing for the free energy or the atomic mobility. That also all the diffusivity calculated from mobility. And so I want to mention that a community has been, CAFAD community has started about 50 years ago, and has an annual conference. As a CAFAD has a private foundation, gives scholarships, and has a journal since 1977. If any of you are interested to join the CAFAD community, you can go to this website and subscribe to the email list we have. And the community is supported by tools and databases. Today, most of the companies in the world, if they deal with materials, they probably use one way or another CAFAD databases and the tools. for the materials simulations. Most of the phase field simulation today use the CAFAT thermodynamic databases, for example. And so we have commercial tools support the industry, and we also have open source tools to support the tool and the theory and the model development. So let's go to quantum mechanics. As we know that quantum mechanics is signatured by the Schrödinger equation, and its digitization is through density function theory. We have ground state configuration. At T is equal to 0, at T equal to 0 Kelvin, there's unique electron density, which gives the lowest energy of the system. We call it ground state. So we can calculate them pretty accurately today. Quantitative, put it this way, without experimental inputs, without direct experimental inputs. And when temperature is higher than 0 Kelvin, we can calculate the entropy of the system, of the configuration, through the electrons, some electrons, in terms of Fermi-Dirac statistics, or the phonons through both Einstein statistics. So we get entropy of the ground state configuration for a specific configuration. And then we calculate the energy of that configuration very accurately, I would say. But of course, some people say, oh, no, it's not accurate because they're comparing it with experiments. The challenge is that we should not compare those calculations with experiments because it only concerns the ground state configuration. So then we go to the top, in the 150 years, thermodynamics, we go to the top one with the Gibbs. Gibbs developed the combined law and the statistical mechanics. So it's combined law is this equation for a multi-component system. And this equation is very, very important. This equation is applicable to equilibrium system only. Okay. So when Gibbs combined the first and the second law of thermodynamics, he actually effectively removed the second law because he was interested in the equilibrium system only. Okay. And then he derived the statistical mechanics. He said entropy of a system is a probability is a combination of a probability of each configurations. The PK is a probability defined by the partition function of that configuration, divided by the partition function of the system, which he proposed this total energy. I'm not apologize. So here that people use EK, but in the combined use U. So it's the same thing here. Okay, it's the same thing. And then total partition function of the system is a summation of the partition function of each configuration. When each configuration has a similar probability equal to number of 1 over the number of configurations, then we get the Boltzmann entropy form. It's KB log W. But now it's clear that the Boltzmann entropy is a special case of the Gibbs entropy. Of course, Gibbs developed his statistical mechanics based on the knowledge which Boltzmann, Maxwell, and Clausius, other people developed. Okay, so it's natural, right? Now we have DFT. Quantum mechanics, we have the CAFAT. Of course, we want to put this together. Okay, we'll do first principle calculations, and we'll do the phonon calculations. So hopefully our model is better. That's indeed. So we have developed this model in last day, as you can see, the last 20-some years, and use the first principle calculation to enhance the robustness of the CAFAT databases. However, as we just mentioned, that the DFT calculations never agree with experiments. Okay, so all the DFT data we took from those calculations, when we put in the CAFAT, we have to refine those data. We have to change this data a little bit using experiment inputs. Okay, that's the reason because we only consider ground state configuration. But in all the experiments, we have more than ground state configuration. So that means we have to go beyond ground state configuration. That's actually explicitly mentioned in Gibbs's paper in 1901. He said the system embraces every conceivable combination of its configuration. Okay, and this configuration are different in terms of the configurations and the velocities, because people talk about the velocity of the particles or atoms. Okay, so that means we have to go beyond the ground state configuration if we wanted to predict quantitatively experimental observations. So However, those non-ground state configurations, they're all symmetry breaking, right? They're different from each other by symmetry. That means you have internal degrees of freedom. So what type of internal degrees of freedom we have? That includes spin, like magnetic spin, electrical polarization. You have short range ordering, long range ordering. And you can also introduce defects, which is the vacancies, dislocations, and stacking faults. But we know that if you can define the configurations, okay, and if they are stable, then we can calculate the phonon of those configurations. So now you see that we have a capability for DFT go beyond the ground state configurations for any systems we ever study. So let's go back to see the entropy from the Gibbs statistical mechanics. As you can see that this equation we have is S equal to minus KB is Boltzmann constant, summation of PK log PK for each configuration, the probability of each configuration. So if you do that, basically you can visualize that this is like a top-down view of the system. So look at the system, it has so many different configurations. So if you can find the probability of each configuration or calculate it, then we can get the entropy of the system. Okay, so these configurations are symmetry breaking. They're different from the ground state configuration. However, those configurations, their entropy is not zero. What it means is that those configurations, each configuration has their own entropy, right? So we're talking about multi-scale entropy. You have the entropy of the system, you have the entropy of each configuration. So what does that mean? That means we have to add them together in order to calculate the total entropy of the system. And what it means is that we can calculate the entropy of each configuration from the quantum mechanics, from the bottom-up approach. So now if I top it down from statistical mechanics, where bottom up the quantum mechanics, you put them together, we got a Zentropy. It's coarse grain of entropy. So now we can calculate each configuration, entropy of each configuration from quantum mechanics. We'll put them together. Then we'll calculate the total entropy of the system. So now you can see that the statistical mechanics we are using, as mostly used in the literature, only have first part. That means the statistical mechanics we have today does not count the total entropy of the system. All right, so let's look at this one. By the way, the entropy name is not recreated. So when I give a talk, 2021, when we talk about our method, we said it would be nice to have a name for our approach. And then somebody suggested we should call it Zentropy. Z is a partition function, entropy. So it's a partition function for the entropy, and you put all the entropy together. So let's compare the entropy in terms of the statistical mechanics in the Gibbs statistical mechanics. We have entropy, we have the free energy, we have the partition function, we have the probability. So you see we have EK here, right? EK is total energy. However, the entropy statistical mechanics basically we should add another entropy here because each configuration has its own entropy. So add them together, then we have to change here from E to F because SK here. Because EK plus EK minus TSK equals to FK. So same thing here, then all the EK must be replaced by FK. Well, that's significant, right? Because FK is different from EK, and then probability is different. Probability is different, so partition function is different. Partition function is different, friends is different. Friends is different, entropy is different. Okay, so it makes a huge difference on the total entropy of the system, which we can predict with this approach. However, this two approaches are actually identical if SK equals 0. So when does that happen? Well, SK equals 0 when the configurations are pure quantum configurations without any unspecified degrees of freedom inside that configuration. Then it is same. That's exactly what the quantum statistical mechanics is about. Quantum statistical mechanics by lambda is for the pure quantum configurations. So it's perfect. But however, if we take a DFT, the configurations we have, even the ground state we have, they are not pure quantum configurations anymore. So that means we cannot apply the standard statistical mechanics to the DFT calculations we have. Okay, so that's basically our theory. That's the first theory we had about statistical mechanics. So I'm going to talk about the reversible thermodynamics later. But let's make some applications. So the first application, we applied the Zentropy theory. At that time, we did not call it Zentropy theory because we didn't have a name for that. For magnetic materials. So magnetic materials, we know that what happens for magnetic materials is that when you increase temperature, you get spin flipping, okay? And spin flipping in the literature, there are two theories, the collinear spin configuration or non-collinear spin configuration, okay? We believe that collinear spin configuration dominates. So we start with a simple one. So first problem we address is cerium. Cerium actually turned out a very hard problem because the cerium is temperature pressure phase diagram. You see that you have FCC phase here. There's another phase, double FCP phase. So let's forget that phase for the time being. So FCC, post FCC phase, alpha and gamma, and there's a critical point here. Okay, the ground state alpha is non-magnetic. It's going to 0 Kelvin. That's amazing, right? Because it's the only element in periodic table which is non-magnetic at 0 Kelvin, and it becomes ferromagnetic at high temperature. Okay, this volume change is huge, like 15 to 17% volume change. Okay. Because you need to expand the volume to get the spin development. And then you have a critical point. Okay. And it has never been predicted completely in the literature. And then, of course, you think about this one, right? If you have the ferromagnetic state, non-magnetic state, you got to have some intermediate state, at least one antiferromagnetic state called AFM. So what we did is that we said we first did two states. It didn't, two configurations didn't work. So we take three configurations. We take the ferromagnetic and the AFM and non-magnetic. You see, we have to add a little U parameter to this one, very small U parameter. So you see that we get the ground state. Then we have the two non-ground state configurations. They both are stable. Okay. So we can calculate the free energy. Then we use partition function, use a Zentropy theory to calculate system free energy. At 0 Kelvin, we have this ground state, this one, right? And then we have another one, the AFM state. You can do tangent here. Tangent give you the pressure. Okay. And then we can do that increase temperature. We get this Zentropy entropy into consideration. We find the two points merging closer and closer. And then at one point, they merge into 1 point. That means now the double wedge disappears in this case, and you get the critical point. Okay, so exactly what happens when you calculate the free energy at a different temperature. Just see how this light blue area is what the extra entropy of mixing of the three configurations. That's statistical mechanics. We can see that at 476 Kelvin, and there's two lines that is the original two state, three. This just show two configurations. But we have three configurations mixed together. You see that this the maximum disappears. And that's where you get a critical point. So you do tangent, you get this pressure is 2.22 gigapascal. So we predict critical point at 476 Kelvin at 2.22 gigapascal. At a high temperature, of course, you don't have this, maybe second order transition. Okay, we'll put them together. That's our printing plot here. Temperature and pressure, you can see that the line is prediction and the symbols are experiments. And it's almost perfect with the experimental scattering. And there's no experimental input. It's completely from DFT with three configurations only. And then we can change the pressure to its conjugated variable volume. Oops, sorry. And you see that you get this phase diagram, TVA phase diagram. You get misfitted gap, get the tie lines, you get a critical point. Then you get this anomaly of volume change. At the critical point, we know that the volume is going to, some expansion is going to diverge. The T to V derivative is equal to 0, V to T equal to infinite. It's positive infinite. And the second case we tested, then we can plot a lot of properties, like this equation of state, the volume as a function of pressure. And because we calculate the entropy we have, I can see that the two is phono entropy, lattice, and somebody actually is the black line, but you have to add this together. So you can say DFT alone is way off from the experiments. You have to add the mixed energy, entropy on top of it. Same is for the total energy calculations. The next thing we addressed is on this negative thermal experience, IMBA effect. Is Einstein Platinum. This experiment. the symbols are for experiments, and the line is our prediction. And we show how to predict that. So in this case, we take a little bit larger system. We take 9 iron atoms. So 2 9.512 configurations, different spin configurations. And because of symmetry, we only have 37 of them are unique, and the rest are the multiplicity. We find the ground state. We found the other configuration, which has a relatively low energy. We can put the total energy together. So this is the 0 Kelvin, total energy function of the volume, ground state. Now you see immediately different. The non-ground state configurations have smaller volume. In the previous case, they have larger volume. So in calculate the free energy, we notice that the free energy, the ground state, has lowest free energy in all temperatures we experience, the experiments. But the difference divided by kBT becomes smaller. That means the probability of the metastable configuration will increase as a function of temperature. So even though it's stable, but only one configuration, but we have 500 configurations, right? So the probability of the ground state decreases dramatically, even goes less than 15% at high temperature, even though it's the low state, free energy state. So we take the 50%. Actually, we did a different method to determine the transition temperature. We can also calculate the Barkham property modular as function of temperature at different pressure. We see all the anomalies, so to speak. Then we put the PT diagram. Again, this with the first order transition critical point and a second order, and with experimental data. Again, there's no experimental input. It's purely for the DFT plus statistical mechanics. The very important thing is that we can also plot the TV diagram. We can calculate the volume as function of temperature for given pressure, this ambient pressure. We can see that the volume first increase, then start to increase less, then start to decrease total volume, and then increase again. So in the purple area, we see the negative thermal expansion. The volume decreases when temperature goes up. And that's not a surprise at all, because at the critical point, it has to diverge, right? So it's negative divergency. So the thermal expansion diverges negative at the critical point for iron free platinum. Now, whereas the reason is because the metastable configurations have smaller volume than the ground state. So the latest problem we just is rare earth nickelate. It's classical strongly correlated physical systems. And here it's just different rare earth elements. And see how the temperature has different, they call it tolerance factor. Basically, is the property of each the rare earth elements. You see that you have the insulator from the antiferromagnetic to paramagnetic. And I was asked, can we use our method to predict the two phase boundaries? Well, we haven't finished all of them yet, but we finished one. We take each one as the case. We predict the transition of this one from the magnetic transition. So the structure is pretty complex, but it has been a lot of calculating in the literature, and you see the structure of them, okay? With the ground state and the rotation of this octahedral sides, and the valence of the magnetic moment of nickel in the rare nickel elements. Okay, so we take each nickelate as the case. So we take 80 atoms supercell, and turn out the ground state is AFM, and this is the blue at the green and the heavy green atoms are all nickel. You see that turned out in the ground state, half of the nickel atoms have no spin. Okay, but the other ones have the up spin and down spin, AFM. Then we can systematically change all spins, right? So we put this as 0, then we change all the other spins. So we get the lowest energy one. Next one is the AFM, we get number 38, is 20.2 MeV above the ground state for the whole unit cell, a supercell. Okay, then you have another FM cell. If you go all of the family, it's very high energy, 121 MeV. We again want to calculate the total energy. We calculate the free energy. We calculate the free energy as function of function of volume, function of temperature. We put them together. We find that we predict the transition temperature when the ground state loses the majority is 144 Kelvin, and experiment 145 Kelvin. Okay. Now we said we're going to test that theory, our theory. If we take the standard statistical mechanics, use the total energy, we find it behaves extremely different. The quantum state decrease much faster than otherwise. So let's see that if you take a DFT calculations, suppose you calculate all configurations. If you take the statistical mechanics with total energy, you still cannot predict experimentally, observe the transition. Okay. So now we can calculate the phase diagram this time, but unfortunately, there's no experimental measurements as far as pressure. So we hope maybe you can measure in the future and validate our prediction. Again, there's no experimental input here. And we can also we develop a calculate short range ordering. So we can see that short range ordering transition actually is very close to the one we talk about is 50%. Okay, this is like 45% of short range ordering. So this just means that this simple criteria actually works very nicely. So the next material work on ferroelectrics. And it took us many years to figure out what are the configurations for ferroelectric. And we realized a couple of years ago is domain war configurations. Okay, so what does it mean? Let's look at the typical measurements we have for ferroelectric polarization of lead titanate. We know that the low temperature, this is X-ray measurement lattice parameters that function temperature. At the low temperature, we know it's tetragonal, polarized. So you have the C-axis and the A-axis. So this is, center line is the volume. The volume decreases, you can see that. Negative thermal expansion. And then at the high temperature, they call it transition temperature. Here you get a cubic, okay? Cubic, you think about it, is A and C are the same, right? So now volume starts to increase, doesn't decrease anymore. So this is X-ray experiment. It's very important. However, people later on use XSOF, X-ray desorption fine structure method. They found that actually it's always tetragonal. It's cross from the XSOF measurements because XSOF has much higher time resolution. It's 0.1 femtosecond resolution. But X-ray we know is micro or millisecond, right? Or microseconds. Okay, but this one is much lower, much faster. So you can find all the titanium atoms, and find that all the titanium actually are displaced. So you have tetragonal and the polarization at the high temperature, way above transition temperature. That's paper is 1994. So the reason because when we do X-ray or neutron, our time resolution is much slower. So you cannot see those things. So what really happens then? Of course, there are theories to do that. And then we said, let's do some simulation. Let's try to understand this one. So let's take a very simple case here. This is cartoon. Shows a kind of bird in a cage, a summer drop. What it means is that we have a cardboard. We have two sides. One side is a cage, and that side is a bird. Okay, let me stop it. Oh. Okay, you see, one side is a cage, one side is a bird. Okay, so however, if you spin fast enough, you observe a bird in the cage. Okay, so what does that mean? That means we observe that the tetragonal at low temperature because we spin very slowly. And high temperature spin very fast, you cannot see them individually anymore. You see average of it. So we'll prove that on by the AMD simulation. So we take the lattice parameter with the one from the experiment, cubic, and the transition temperature. With the cubic lattice parameter, we take 150 atoms. We do simulation. What do we see here? Well, even though there is cubic overall, but the local titanium atoms is going up, going down, going sideways. Okay. Well, we realize that this simulation time step is 3 femtoseconds. Okay. So we can see them. We can see those. What happens? The tetragonal goes like this. It goes like that. It goes like different directions. So it's all this polarized with tetragonal shape. So most of the nucleus are tetragonal. That's what XSOF observes. Okay. So we can actually quantify. We see at 753 Kelvin, you follow titanium. You see here, then jump like to that direction, right? So you see there's different atoms jump all the time. But the time scale, again, this is 1,000 steps, right? That's 1,000 steps, each step is 3 femtosecond. So there's 3,000 femtosecond. Okay, so X-ray cannot see that. If you go low temperature, you see that they change this flip less frequently. If you go low, then you can see now, right? This is like 3,000, but for you go low temperature, you can see it. So X-ray can see that. Okay. So if you now compare the AMD simulation and the XSAF, because AMD used the experimental parameter, okay, but XSAF is direct measurements, okay, local measurements. So it means actually at room temperature, you already have a lot of mixture already. The flipping happens already. So actually the local structure is all tetragonal, polarized. But when you do the X-ray, you see a cubic structure because it cannot resolve this high frequency flipping. So now again, you do the polarization, titanium. Again, you see the red one is from AMD, the blue is from XF, and the green is from neutron, and the black is from X-ray. So neutron X-ray is average. The average is observation, what happens in the cinema. Again, just because the resolution is different. So then we found there after many, so our simulation was done in 2015, right? We did not make any progress. Because we're still trying to figure out how to define the configuration until very recently. Actually, our paper is published in 2023. And we found that we can define just these 3 configurations. The ground state configuration with phono, then 180 degree, and then 90 degree domain was. Because when the polarization change direction, you can change this direction, right? Then you get 90 degree. If you change up and down, you get 180 degree. That's only 2. So it's very simple, actually. So we take this 2, we can predict the transition now. We didn't do calculations yet. We didn't do the DFT calculations. We take the domain wave energy from the literature. So it's 35 millijoule per square meter for the 90 degree, 132. This is from the Vanderbilt's work. And then some more recent work is 29, 114. So it's lower. This is lower. Well, so you can see that it's actually the higher one because it agree with the experiment better. The low one, it does not. Of course, they are 0 Kelvin. So we are not calculating the phonos, trying to make them better. All right. So what is entropy theory? We have 3 ingredients for that one. First, we need to get a ground state and symmetry-breaking long ground state configurations. We need to calculate the free energies. That means they must be stable. And then with the partition function of configuration with their free energies, that's very critical. If you use total energy, you get wrong results. And then we can do quantitative prediction without models, without fitting parameters. And even can calculate the energy landscape as showed for Syrian. You can calculate equilibrium, you can calculate all kinds of properties we're talking about it in terms of derivatives of the free energy. Okay, so let's talk about the quantum mechanics and the statistical mechanics and the Zentropy for prediction. So what about the irreversible thermodynamics? Which is about entropy production due to internal processes. Okay? And entropy change and entropy production are 2 different things. Okay? But entropy change involves 3 terms: the heat exchange, the mass exchange, and the entropy production is only this term. Okay, so that's the change of entropy change of the system has 3 components. Okay, so if you put this one into the combined law, we got this equation. So the internal energy is a function of entropy, work, and chemical and entropy production. Okay, so chemical potential is a function of. It's important to realize chemical potential has entropy in it. That has never been clear in the literature. So in the Gibbs equilibrium thermodynamics, plus term equals 0. So irreversible thermodynamics, last term is not equal to 0. It's larger than 0. Okay, that's why Gibbs cannot treat it, because you cannot treat it since larger than 0, right? Inequality, not equality. Okay. However, we can define it. We can define the entropy production times temperature is the energy at the production equal to different process. You have many internal processes. Each one has a driving force. Each one has a variable to describe the extent of that internal processes. Now we can put in the equal term now. That, I think, is a major contribution by Professor Max Hiller, and you can put it in there. So let's talk about entropy production. Okay, so entropy production again has 4 terms. That's what I wrote in one of my papers and also in my book. Is that you have 4 contributions for each process, 4 actions. Firstly, the process can generate heat or absorb heat, so the heat. Second one, it can absorb some components and they produce some components, and then it has a configuration change. Okay, put them all together, it has this driving force with the internal variable that describes that process. Okay, so we can actually very easily look at this one, right? For example, we have this lot of empirical laws. We have Darcy's law, we have Fourier's law, and Ohm's law, and the fixed first law. Okay, and the equation here is very important. I go back to this one. Is that we have conjugated variables. The Ts and the mu ni t di, they're conjugated variables. Okay, we divide by y and x. So when we talk about this empirical laws, these 2 laws are about conjugated variables. So this is the pressure, this is volume. Okay, this is the electric field, this is current. And current is electrons. So this is conjugated variable. So actually, the heat flow is actually not accurate. It's not really a heat. It's entropy flow. We change the entropy flow. Of course, entropy is related to heat, but entropy is not only heat. But most time, we just approximate it. So mostly we should change this equation. This equation is inaccurate, the best state. We should put a chemical potential gradient instead of concentration gradient. But of course, we can change the concentration gradient, then we have to have more concentration gradient than 1 term. So Gibbs fixed on 1 term, that's inaccurate. Actually, it's most time is wrong. Okay, so this is the direct phenomenon we're talking about. But also it's cross phenomenon. What do we mean by that? Okay, if we get free energy from the Zentropy theory, then we can do direct phenomena between the conjugated variables. The cross phenomenon is what we study the most, actually. Well, not most, is much more than the direct phenomenon. It's between non-conjugate variables. For example, if you talk temperature gradient, the direct phenomenon is the heat and entropy flow. It actually should be entropy flow, entropy conduction. But the cross phenomenon is the electric current, atomic diffusion, volumetric flow. If you have electric field, you have a current flow. Then you have the cross phenomenon, heat conduction, atomic diffusion, strain. And then you talk about strain, pressure, field. Your direct is volume flow, fluid flow, or stream flow. But you have a lot of cross phenomena. Look at this one, right? We have 3 cross direct phenomena. We have 9, okay? At least 9, right? We have 9 cross phenomena. And the diffusion depends on the elements. It's going to be extended dramatically, right? It's going to be 10 components have 10 diffusion, okay? So it's a lot more cross phenomena than the direct phenomena. That's why the cross phenomena is so interesting. Okay, so how do we solve this problem? That's what the irreversible thermodynamics comes in. That's the Onsager flux equation. Onsager says flux of a component of the molar quantity, like for example diffusion, is a function of all gradients. Okay, temperature, pressure, chemical potential, everything, electric field, right? Because that's observed. We observe that. And then Onsager went 1 step further. He proved that this matrix is symmetric. And then if you write this for diffusion, okay, that means you at least have this one, right? Actually, I have a lot of more chemical potential here. Okay, yeah, a lot more chemical potentials. So that means you have a lot of diffusivity. Okay, so is that right? So can we have more diffusivity for one component? Experiment observation says yes, you have, because you can drive the diffusion by electric field, right? So that's coefficient here. Okay, however, when I was a student, I learned that there's only 1 diffusivity per atom, per element. That's called atomic mobility. That's actually my PhD advisor's PhD thesis. And then we also know that it can read the trace diffusivity. There's only 1 trace diffusivity per element. You don't have more trace diffusivity. Okay. And that is the mobility related to the error parameter by the driving force chemical potential gradient. However, if we change to concentration gradient, immediately we got a matrix now. And then we can also go into this intrinsic diffusivity, we call it. Another thing that when we talk about diffusion is moving system, right? So if you change the frame of reference, you get another matrix. Okay, so let's see, from one diffusivity, one kinetic coefficient, it can be a matrix by changing from the chemical potential concentration, because chemical potential of Y element depends on all other concentrations. And the same thing, if you change reference state, a frame of reference for the diffusion, just like relativity. If you're inside the system, outside the system, you get different value. Okay, so you become matrix. Then, of course, you can change the concentration gradient because that's you typically measure. Then you get the interdiffusion coefficient. So from the one parameter, you become matrix, right? So what is the difference between these two? It's thermodynamics. It's the second derivative of the Gibbs energy to compositions. So that means I couldn't understand at that time when people told me during my sabbatical in 2014, they said there are so many diffusivity for each element. Then I tried to dig it out. Okay. Of course, I'm not the first one to find out the problem. They discussed many in the literature a lot. So Truesdale was one developed the most critical to Onsager relation. He said Onsager relation is self-contradictory. Okay, he actually talked about, he had a book on 6 lectures on modern natural velocity to say Onsager is wrong. Okay, then he developed called rational thermodynamics in the 1960s. Unfortunately, it didn't pick up by the community, while some people studied, but very few. And then when I was looking at this problem, I looked at literature, I found these 2 papers by these 2 authors, very interesting. They showed that chemical flux of a component is only a function of the gradient of chemical potential. Okay, that means this equals 0. That means the Onsager equation, the flux should be symmetric. Okay. And then Masita pointed out that the Onsager relation is not fundamental physics, it's phenomenological. And everybody says it's phenomenological, it's not fundamental. But however, there's no solution. How do you solve that problem? How do you make it more fundamental and make it as good as first and second law of thermodynamics? Okay, so that's what I picked up as a problem during my sabbatical, 2014-15. So in the last 8 years, 6 and 7 years, I've been looking at this one and all the time. Okay, then ask the 4 questions about this one. The first question is that if Onsager is right, that means he talked about this symmetrical. Symmetrical matrix can be diagonalized. If you diagonalize the matrix, what is the eigenvector? That's the first question. Can we fundamentally tell what the eigenvector is? Second is that it's macroscopic reversibility. That's what Onsager used to derive his symmetric matrix. If that's the case, then you have to apply Gibbs to Henry relation. That means not all the potentials are independent. In that equation, you cannot write all the potential equations to start with. At least one will have to be molar quantity. So that means his equation itself is self-contradictory. The third one is that if there's no driving force for internal variable change, okay, but it could still have a flux, right? So that means what it drives. Of course, people say, oh, diffusion driven by temperature, right? But the temperature makes the chemical potential is the same. So how could the atom still move? Okay, suppose it can move. So you have no driving force. Flux times driving force equals 0. That means you have a non-zero flux, but no entropy reduction. But that's against second law, right? When second law has to produce entropy. Something change has to produce entropy. So it's a change, but no entropy production. So that's again, so put those 4 together. So we come up on this entropy production, okay? And driving for the flux. We know that in this combined law, there's no cross terms. It's only terms between the conjugated variables. Same thing with here, right? With same events change, you have to try to conjugate a variable, potential of that change. Okay, so that means it's very clear. Now you can write the entropy reduction rate, and then is the change of this process. Then you immediately got this equation. It defines the driving force, then defines the flux. So this one drives that flux alone. So you can write this immediately. And these two terms come into the combined law, and without any problem with the second law. Okay, so that means for the combined law, we can give a set of eigenvector directly. Okay, without any constraint, without any problem to do that. So then what it means is that then we have to explain how to observe temperature driving diffusion, right? Or temperature driving current. Okay, so what we'll do is that let's look at this flux equation. So flux has no cross terms, just like combined law. And any flux of a molar quantity driven by its conjugated potential gradient. And you only have one kinetic coefficient. However, the potential gradient of that one, the variable, is a function of all other variables. Depends how you control it. Could be its own, of course, its own molar quantity, and the other molar quantity, other potentials. So this gradient can be used the chain rule to extend to the gradient of this one, its own molar quantity, gradient of other molar quantities, gradient of temperature, or gradient of potentials. Of course, we don't have to have the middle one, right? So you see, we at least have one molar quantity as a gradient. So we fulfill all the required problems we had for the Onsager relation. And the flux will be same thing, right? Flux now will be driven by the potential, the composition, for example, or the another molar quantity, or the potentials. For example, that's what the fixed law is inaccurate, because fixed law only have one term, but in reality you have so many more terms. Okay, so fixed law actually is wrong. Most time you give wrong results. Cannot be quantitative at all most of the time. So this way now we can show that one. I can show it works, at least theoretically. So then how do we test it? Right, you can test it. Okay, so before we go test, we need to understand the derivatives of free energy. So this is our combined law. So we talk about the derivative between the conjugate variables. It's always positive for a stable system. For example, temperature entropy. But between non-conjugate variables, like the YB or T, temperature to volume, they could be both negative or positive. So that's why I have a negative sum expansion. So negative sum is not anything special. It's just because the nature laws do not require it to be positive. Okay, and it becomes negative because the metastable configurations they have smaller volume. So it's nothing strange. It's actually the instability is really not this fancy thing about a singularity. It doesn't exist. Now, of course, the free energy derivatives, right? Free energy derivatives come out very important. They actually do derivatives. This is the new derivatives, very well studied. It's between potentials. Okay, I'm going to have one example for that. Then you have linear electro-optical Poker effects with the solid derivatives. So a lot of the properties we do actually can go to the derivatives, like a solid coefficient, a Seebeck coefficient. I'm going to mention in a few minutes. I have 3 minutes to finish it. So these are the properties we have. You see, the derivatives. It's all secondary derivative of the free energy. The diagonal terms are positive. For a stable system, so off diagonal terms could be positive or negative. Okay, no requirements to be positive or negative. So last row here is very important. Okay, this is between two potentials. Okay, so if we put all the two potentials together, we find this another property. So you see, you can do stress to temperature. That's some expansion, right? Electric field to temperature. Okay, that's some electric. Okay, so you can a lot of things come, all the properties we can calculate them. Okay. So we're going to example. We do example some electric we did last 2018. So if you know the thermoelectric property, you do that at the beginning. You have no temperature gradient at time 0. So everything is homogeneous. No chemical potential, no concentration, electron difference. So when you start time, okay, add a temperature gradient. At that, suppose the electron has not migrated yet. Well, I actually migrated. I suppose it didn't migrate. So it's have the same composition everywhere of electrons. But now because temperature difference, the chemical potential of electrons are different. Okay? So now, because the chemical potential different, the electrons start to move, right? So when electron starts to move, it will get a concentration dependence, okay? But because it has not reached a steady state yet, so you still have the chemical potential of electron difference. When time goes long enough, you don't have a large electron current, so you get a zero flux of electrons. At that time, the chemical potential electron becomes zero. It's balanced by temperature gradient and the concentration gradient of electron. So you make this equal to zero. Okay. So at the end, you have a non-equilibrium electron distribution. Then you induce the voltage in the middle. So we measure the voltage, we measure the delta T, we calculate the Seebeck coefficient. That's how to do experiments. Now, how to do theory? Theory is that we get the flux equation of the electron. Its current should be only depends on its own electron chemical potential. Electric can be the function of concentration of electrons and the temperature gradient. So you can solve the second derivative, right? There's two second derivatives, and the second derivative is partial entropy. Okay, very important. So now we have the steady state. There's no electron flow. So then these two balance each other because the electron difference gives you the voltage difference. Okay, so then we can get Seebeck coefficient. So Seebeck coefficient is completely thermodynamical property. It's just a partial entropy of electron with minus sign. And if you take this one, when the electron moves, it carries heat. Okay, so you can get the Peltier coefficient and Thomson relation immediately without any assumption. You can also do the p-type, because the whole, take the partial derivative of the wholes, you get the Seebeck coefficient of a whole. So we did the calculations for the terabyte, and both p-type and n-type, n-type and p-type, and very nice agreement with experiments. And again, no fitting parameters, no models even. And also for the tin selenide, and there's the nanothalene terabyte. And then, so what it means is that we can really predict now, at least for what we have now, right? Of course, there are many more properties we can predict. So we hope we can continue to work on that. So to do this, we need to do a lot of tools. So we develop a lot of tools. We developed the data generation tools, the DFT, machine learning, and the Python entropy is on development. We also compile experiment data for comparison. And then we can use them to evaluate databases, develop databases, and then we do inverse design. We also do the workshop, training workshops. Okay, with that one, I want to close my talk. I think we have two theories now, which can be quantitatively predict experimental observations. One is Zentropy theory. It's a predicted free energy landscape through integrating quantum and statistics thermodynamics, and it can predict heat capacity. And we have another theory, a theory of cross phenomenon, which can predict the coefficient of both phenomena, mostly cross phenomenon, through free energy barriers between the states and the second derivative of free energy, which shows through this flux equation, which corrected the phenomenological equation by Onsager, and then we can quantitatively predict the cross phenomenon through this second derivatives of free energy. Thank you very much.